So, as I mentioned, there was a couple topics from previous units that I wanted to roll into your brain because they'll absolutely be tested on. The two units that I'm pulling from are Unit 6 and Unit 12, which statistically are usually two of the most unpopular units of the year. It's the last unit of each semester. Unit 6 was solution equilibria, so you're going to hear me talk about buffers and titrations, while Unit 12, as we just finished, was electrochem. So I could have folded electrochem right into what we were doing, but I'm a creature of habit, so everything ended where it did. Plus, y'all made hundreds on your electrochem quiz for some reason that I'm still figuring out. So I'm glad y'all think it's the easiest chemistry ever. I bet you'll get every one of those questions right on the AP exam, right? Now, of all the things I have to show you today, there is a sad moment. So this might make it so some of y'all can't sleep tonight. And I apologize if that happens. But this is the very last time that you get to see my rooster friend here. He's gone. And every year, whenever it's time to see him for the last time, we have to exterminate him. What do you think now? Anyway. Okay. Are we okay? We can move forward? All right. Let me bring you back to December. We ended the first semester talking about titration. So follow along with your brain because the whole point of everything starting tomorrow is going to be to revamp everything anyway. So let's get rid of the cobwebs. When we studied titrations, you actually did one. You did a lab where you had an analyte. It was an acidic solution that I didn't give you details on what it was. Then you had a titrant, which you knew exactly what it was. It was a base, all right, and you put it into a burette and you added the base to the acid, titrated it. Now, the only way that the data worked was that you had an indicator inside the analyte, the acid, that would change color once the solution began to turn into a basic environment. The indicator is clear, or it was phenolphthalein. It was clear in the presence of hydrogen ion, but pink in the presence of hydroxide ion. So as you started with that acidic analyte and you added the indicator, nothing happened. And as you titrated and added drop by drop of your basic titrant, you waited until there was a moment where one of the splashes made the solution go pink for a moment and disappear, and you knew you were close to an equivalence point, which we'll go back over that vocab in a moment. And then the whole point was to make the color change pink the lightest possible without going back clear, and you knew that you would be right at that moment where you could find out all the numbers you didn't know about the acid by running some of your titration math. On the board while we were doing titrations, on Schoology, those were like the 5-part questions where it would say you start with the weak acid and a strong base or whatever, and you titrate it, and it would say, what's the pH after you add 5 mils? What's the pH after you add 15 mils? What's the pH if you go 5 mils plus past the equivalence point? All those types of questions that you're going to need to review because you need to be able to do it in 2 weeks. But what I didn't show you is that there is a thing called a titration curve that represents the data that goes along with that information, all right? And this was the only, I could pick one slide and save it, so this is the one I picked since I can't use my computer right now. But those are what titration curves look like. And but it says it's a graph that plots volume of titrant against pH. And what you'll notice is that the pH is standing on the y-axis, and then as you add the titrant, the thing that you know all the facts about, to the analyte, well, the pH starts to change. But the shape in which it changes is not linear. It makes that predictable S shape, as you can see in these graphs. So really what I want to do, since I skipped showing you these titration curves, is there's a few main angles that AP likes to ask questions on them. So I want to point out those ways. So be ready to jot down and work along with me, of course. Some of y'all are way too comfy. One of the common questions that they could ask you about a titration curve is, what's the general identity of the analyte? All right, now let's keep in mind that when I say analyte, I'm referring to the dude that's in here. All right, this is the analyte, the one that you are trying to find out more about. Usually it's molarity. All right, let's finish this picture real quick. All right, and then you've got your titrant. All right, is the dude that's being added to the analyte. Anyway, the first thing I want to point out about the curve is that if they ask you what is the general identity of the analyte, what they might be asking is it a strong base, a strong acid, a weak base, or a weak acid? And it's real easy to figure out if you know what you're talking about. I mean, if you just slightly studied it. But what you want to look at is the origin of the line. All right, notice how these are two different graphs. All right, the two graphs on the slide I most recently showed you are two different curves. But in the first one, notice how the origin is way down here, all right, with a pH below 7. And here the origin is way up top, a pH above 7. So the general identity of your starting analyte should be very obvious based on where that line starts, below 7 acid, above 7 base, right? But strong versus weak, well, that's going to depend on how far, all right, how much on the pole it is. In general, we can just assume that pH 2 or less is a strong acid and pH 3 to 6.9 is a weak acid. Same with the bases, all right, bases 12, 13, 14 are going to be your strong bases, and then below 12 down to 7 would be your weak bases. So I've seen that multiple choice question. Just gives you one of these graphs and wants to know the general identity of the analyte. Those are the 4 choices. So here it looks like we're dealing with the first graph being a strong acid because it's way down below 7 starting, and the second graph being a strong base because it's way above 7 starting. So that would be the first idea that I'd like you to know. Then there's always a jump, all right? Notice how there's kind of a plateau when the titration starts and another plateau when the titration is ending. And then there's that big jump that there will always be. So here's your next big vocab word. Halfway in the middle of the big jump is the equivalence point. Now, equivalence point is not new, the middle of the big jump. Equivalence point is not a new concept for you. If you remember, it was when the moles of analyte matched the moles of titrant. One of the things we kept in mind while studying titrations is that the moles of analyte never changes, right? We started with a set amount of analyte, we could figure out how many moles that was and not touch it again. But the moles of titrant that were present were constantly increasing, and that's a number that we had to keep up with, all right? So the equivalence point was the moment where you added enough titrant for the moles of both to equal each other. What I'm telling you is if you're reading a titration curve, that point is in the middle of the jump. Now, this can indicate some other things for you. So I almost tried to change the slide. Such as the identity of both of these dudes in regards to strength. So on this one, what you can't see up there, but if you look at your notes, you can, is that these curves I keep showing you is a strong. Now, we learned, it was engraved in your brain, it was an absolute, that if you titrate a strong with a strong, that the equivalence point has a pH of 7. That's always true. So you can see that my two graphs here are matching that data, that the midway point of the jump lives at 7. But if we change to a different combination of titrant and analyte, this example is a strong acid mixed with a weak base. And what you'll see is that the equivalence point is no longer at 7. But where the equivalence point moves to is totally predictable. So keep in mind, in this example, we're saying the analyte is a strong acid and the titrant is a weak base. Well, that means that your starting stuff is much stronger than the stuff that you're adding to it. So once you get to the point where you've got equal amounts of them, but the acid is way stronger than the base, then we would expect the equivalence point to be less than 7. We would expect the equivalence point to be acidic. Not only that, the slide that I just showed you used ammonium and hydrochloric acid as an example. All right, it said that if we're doing this weak strong, what if this was NH3 and this was HCl? All right, weak added to strong. Not only is the equivalence point going to stay acidic in this situation, but we know that if you're analyzing the pH of a weak sample, well, ammonia doesn't completely dissociate. We know that if we're going to look at a resulting, should not use the, oh, I should see it. If you're going to look at a resulting pH of ammonia doing things, that the weak samples are analyzed Bronsted-Lowry in water, in which case the base is a proton acceptor, of course. So this is the interaction that we consider where hydroxide is certainly made, which is going to encourage the pH to be rising because that's basic, but this ammonium ion has acidic nature to it. So not only is the pH going to stay relatively low in regards to the equivalence point because the HCl is much stronger than the ammonia, but one of the products of the NH3 being added is more acidic species. All right, so yeah, it's making this OH minus that is going to make the curve go up towards the base eventually, slowly. But the fact that it's producing a byproduct that is also acidic in addition to the acidic HCl is going to just still keep that curve nice and low. All right, and then the other curve that I show is weak acid, strong base, right? And it does exactly what you would expect it to do. So think about it again. It's switching this and it's saying, what if this acid, what if the analyte was weak and the base was strong? All right, well, if you start with a weak sample, first off, the origin of the graph, you'll notice, is closer to the 7 because it's a weak acid, right? It's further up. So that's one way to know that the analyte you're starting with is weak. But if you start with something weak and you start adding something strong to it, well, when it hits the equivalence point, we're going to expect the pH to be above 7, right? Because it's starting below 7 because it's acidic, but it's weak. We're adding the strong base. It's going to pull up faster than it would if it was vice versa, like in the previous slide. So based on where that equivalence point lives, you can identify weak versus strong for each of the samples. And Schoology will give you practice on doing that. How are we doing? Y'all are very, very quiet. We're glad Unit 6 was a long time ago. This slide I showed a moment ago has another vocab word on it. It mentions the buffer zone. So I'd like to mention that these plateaued areas, all right, it starts with that flattened, somewhat flattened area and it ends with that somewhat flattened area. In most cases, there's a buffered system there. Now, if you remember what a buffered system is, it's going to be that scenario where a weak sample and its conjugate pair are both existing in the same solution, and they can resist pH changes when intruders come. I used your blood as an example. The reason that it's not a linear line, all right, the reason that when you start the titration that it doesn't just start, okay, here we go, we're adding hydroxide, is because in that buffered system, it initially resists the change. It starts to change a little bit, but it puts up a fight before that pH starts to change. But once you break the buffer, right, remember the buffer is not perfect. We can't just drink hydrochloric acid because we have buffered blood. Eventually the buffer breaks. Once the buffer breaks, then it's like, whoa, okay. And then you build the opposite kind of buffer. It starts to plateau again because now the contents are going to be in that first example that y'all can still see. a basic buffered solution. So we call that the buffer zone. But even though some of y'all are already numb to me talking, I'm sorry. Here's the most important thing for this first part that I'm going to say. So listen. Of all these different angles they can ask you questions on, and I've seen all of them, here's the one they ask most commonly. Do you remember what pKa is? Let's take it letter at a time. K is an equilibrium value. Ka is an equilibrium value of an acid. pKa, what is it? Mathematically, what's it mean if you put a P in front of something? You're almost right, but it's not just the logarithm of it, it's the negative log. All right, it's the negative log of it. All right, so pKa is the negative log of the equilibrium of an acid. God, this class is awesome. We calculated pKa's usually using Henderson-Hasselbalch when it came to buffers and stuff. But you can find the pKa without doing math while looking at one of these curves. And this is their favorite question about these. It's on this next slide. All right, it's the very bottom point, but it's called the half equivalence point. All right, the half equivalence point is basically the middle of the plateau, but it's also the halfway point of the equivalence point. So if I go right here, if the equivalence point was here, then theoretically, the half equivalence point will be right here in the middle of the plateau, and which will also equal half of that value. At this point, the pH and the pKa are the same value. All right, so this tells that axis tells you the pH. So my point is that if you know the equivalence point and you can find the half equivalence point, which is living in the middle of the plateau, and they say, what's the pKa? Well, to the untrained mind, you might be like, what formula do I use for that? No. The pKa, got it, yes. Oh, they need them right this second. Okay, thanks. Should I say their names so you're famous? Yeah? Everybody's in? I need Leslie and a Stephanie to please come take these from me. You want to come? Do you want to come wave hello to the people? You don't have to. All right. No? Come wave. Come wave. Yeah, this is. Yeah, look. These are students. Okay. It says immediately, so I guess it's more important than I am. Anyway, the pH value is telling you the pKa value at this one specific point. And I don't want you to miss those questions when they ask. Again, Schoology is going to give you practice, but what you think? I'm about to change gears dramatically. We sure we're good? Yes. I'm thirsty. This is from first period. You think it's still good?
Yeah. You can leave it up.
Yeah, I left it up. It smells like a dead baby. It tastes like one too. Okay. What? I keep trying to change the slide. Now what y'all need to do is y'all need to go onto this video and alter just that one little quote for me and like put it into like a rap song. Smells like a dead baby, tastes like one too. Anyway, it'd be cool. I hate working here anyway. I'm just kidding. All right, let's fast forward to Unit 12. Now, Unit 12 is what we just finished, and there is one formula that I did not put into the unit. So this I equals Q over T, which you have already copied down because you're so brilliant, is on your formula chart. I just need to show you how to use it. Now, this is a measure of current. So during electrochem, we looked at cell potential and stuff like that. We measured voltage, but current is different than those things because current looks at the amount of electron energy that's coming through, which is different than the amount of electrical energy that's coming through. But really, the use of this new formula is stoichiometric. All right. The very last thing that we looked at in electrochem was electrolysis. All right, which is going to be those, those cells that required energy input because they weren't thermodynamically favored. But one of the things that we were doing that we didn't really focus on was we were writing half reactions, right? We were writing all these half reactions throughout the unit, but we never looked at them stoichiometrically, and that's what this equation will do. The only difference, so it's just stoichiometry, right? And plus this equation, they're going to marry each other. But looking at the stoichiometry of electrochem, in regard to current, it's a little different because one of the conversions you can do is with the electrons. If you look at your half reactions, right, we had a number of electrons that would show up to balance each other on each side. And we can put that into a dimensional analysis grid to help give us things like coulombs, right, which is our different units of energy. So I just want to show you what that looks like. It feels a little different, but it's pretty much all the same. So in terms of the labeling of your equation, all right, it's basically current equals charge over time. And your slides have the units there. I've also got them written on the board behind me. The time has to be in seconds, all right? The time must be in seconds. They really like to give you problems that have minutes in it on the AP exam. So if they say that it takes place in 2 minutes, all right, how many seconds is that? Boom, did you hear them talk? 7th period's alive. Anyway, yeah, don't put minutes into the problem. It's a very common practice of there. So I just want to show you how to use it. We've got 2 problems that we're going to do, and we will call it the end of everything. So hopefully you have these in front of you so that you can work along with me. All right, it says, how long must a current of 5 amps? Amps is going to be our new unit of I here to find current. How long must 5 amps be applied to a solution of silver to produce 10.5 grams of silver metal? Now, let's remind ourselves real quick what the heck that's even talking about. This is referring to electroplating, right? I mentioned it a couple times during the unit that one of the worldwide uses of the electrochem is to harvest metal, right? Like sodium. You can't go find sodiums that's in the solid form. You have to make it during the processes that I have been showing you. All right, well, we don't just say, okay, well, let's electrocute some sodium ions and hope we get enough. No, of course it's not like that. I need exactly, in this case, 10.5 grams of, it's saying silver metal. So how long do what voltage, all right, or at what energy, not voltage, and for how long does the system have to go to make exactly how much you need? And so it's very real life and practical, the use of this. So follow along with me on this first problem, and I think you're going to do just fine. Now, it's dealing with silver. As I said, this is a stoichiometric look, and we know that we can't do stoichiometry without an equation. So this is going to be using, as it says, silver ion to create silver. Now, I said silver ion, but I didn't make it an ion yet. Who knows the charge of silver? It's just +1, all right? So there's silver, all right? You are supposed to know that. Silver's always +1, zinc, and what else are always +2? No. No. Tell me that had to be on purpose. Lead, it ain't lead, stupid, it's PB. Cadmium. Cadmium's the other one. Anyway, now, but for this to become this, it's unbalanced. What is the reactant side missing? An electron, all right? So there it is. All right, we've got our balanced equation. All right, and we can start working out the problem. So if we take a look, now remember you've got your equation in front of you so that you know where all my stuff is coming from. It gives me the amps, it gives me the current, and it says that is existing at 5.00. But I don't have the other 2 items, all right? I want to know the time. It wants to know how long do you have to do it for. And it gives me grams, it gives me mass, but there's no room for that. But here's what you can do. Using the equation, we can use stoichiometry to turn grams into the coulombs of charge. And that's the stoic I want to show you. All right. So we've got this here. All right, we're looking for time, but we're not ready. Let's do some stoichiometry to get this number. All right, so it's going to start me with what? 10.5 grams of silver. So here we go, 10.5 grams of silver. Remember the trick of stoichiometry. We must always start with what unit? You got to have moles. All right, you have to have moles of given. So let's go from grams of the given to moles of the given. All right. Once you have moles of the given, you can go to moles of whatever else you need. For us to get to this electrical charge, I need the electrons. So we're going to go from moles of the given to moles of the electrons. And then from moles of electrons, we can go to the charge that they carry, which are given in units of coulombs. So there's the top part of my grid. I'm going to bring down all my diagonals. Grams of silver, moles of silver, moles of electrons. David, I don't really have to move you, right? Okay. Oh, dang it, I didn't hit record. I'm just kidding. I've been recording. I appreciate that look on your faces, though. All right, now, do we know our conversion factors? Hopefully we do. Watch how it goes. Moles is over grams. What's the number for moles here? Yay, what's the number for grams? Periodic table. 1 mole equals molar mass of grams. So I didn't have you get it out. It's 107.87. All right, so this is super review. This is honors chem right here, this filling in of conversion factors. Hey, whenever it's moles over moles, where do we always get the numbers from? Yeah, the coefficients up here. And we're already balanced, so what is the coefficient of the electrons? 1. And what's the coefficient of the silver? Oh, sorry, 1. All right, now this one won't always be a 1. If I had given you aluminum, if this was aluminum, how many electrons would we have needed to balance out aluminum's charge? 3, because aluminum's charge is plus 3. So it would have taken 3 E's, and that would be a 3. So realize that I don't want you to think they're always 1s just because my first example is stupid. Coulombs over moles. Hey, check it out. Coulombs over moles. There it is right there. 1 mole of electrons is Faraday's constant. All right, multiply across the top, divide by the product of the bottom, and I get 9390. Stop me if you don't like something. All right, so now my 9390 coulombs is my charge. I have my Q value. And this will spit out time, right? So ultimately, it's going to be 9390 divided by 5. That's what you should be doing with your algebra, right? I saw an FRQ once that had a problem that was incredibly similar to this, but it said express your answer in minutes. All right, so 1880 divided by 60 will give you minutes, right? So just make sure that don't let them outsmart you at the end. But yeah, but it's cool to know that at this current, that if you just let it run, if you set up the experiment and let it run for exactly this long, that minus experimental error, you'll end up with 10.5 grams of silver on the electrode. I think it's cool, even if you don't. Let's do the other one. I'll flash this up there for you again, but let's look at number 2 before we close out the school year. Got it. Number 2, it just asks it backwards, but I like you to have it in your notes. Okay, this one we're only going to run for 200 seconds. That's not very long, all right? Do you think we're going to form a lot of metal or a little bit of metal in 200 seconds? Not very much, usually, all right, unless the amps are really high. And we're looking at zinc. All right, so right away, we're analyzing zinc, and I know that to calculate current, I have to do stoichiometry. So let's look at zinc ion, all right? It's going to be plus something. All right, needs to give me solid zinc. What is the charge of zinc? 2. So how do I balance out the charge? There we go. All right. So you have to know how to write that reaction in order to move forward. Now in this problem though, both of the numbers they give me, the 200 seconds and the 0.25 amps, they both fit right to the equation. All right, that's why this one's kind of backwards. So I can use the I and the T to find Q immediately. And if it had asked for Q, all right, if it had just asked for the charge in coulombs, that would be enough. But of course it wants grams, so we're just gonna have to go backwards. But anyway, so let's plug and chug. We're at 0.25 amps. So let's go 0.25 amps equals the Q we're gonna find. All right, divided by a time of 200 seconds. All right, so ultimately, when you figure out the algebra, it should just be 0.25 times 200, right? Did you get 50? All right, got 50 coulombs there. But it doesn't want that, it wants grams. So let's, same thing, all right, go through the steps. Let's start with my 50 coulombs. And let's get to grams. All right, I know that from coulombs, I can go directly to moles of electrons. All right, because that's what Faraday does. From moles of electrons, you can go to moles of anything in the equation. This question wants to know grams of zinc, so let's go to moles of zinc first. And then, of course, moles to grams. Bring down all the diagonals. Too early for that text. All right, if I'm comparing moles to coulombs, I know that that's Faraday's constant. So 1 mole is 96,500 here. If moles is over moles, the value comes from the coefficients of the balanced equation. For zinc, it's 1. For electrons, it's 2. Grams over moles will be periodic table over 1. You will have a periodic table, but I'll let you know that this is 65.38. And this grid is going to give you a final answer. Say again? No, all molar masses don't follow sig fig rules. We just know that molar masses and percent compositions always go 2 digits past the decimal in AP. The only one that's weird is anybody want to yell out their answer? Perfect. Right, and just as expected, I mean, what's the heck of running it for 200 seconds? That's not even 1/10 of a gram of zinc that we formed on the electrode.